All right, so summarizing what we talked about in class yesterday, we said that when we think about kinetic energy, there's now two ways that we need to think about it. So we know that kinetic energy is energy due to the motion of an object, but now we can think about kinetic energy sort of in two pieces. The first is the object's center of mass moving? If so, then we need to keep track of translational kinetic energy. If the object is rotating about its center of mass, then we're going to need to keep track of rotational kinetic energy. And so the simplest situation is just here's some ball as it rolls down the hill. And what you notice is the center of mass that's given by this dot, it clearly moved. So I've got translational kinetic energy. But as the ball rolls, there's also rotational kinetic energy as the ball rolls about that center of mass. And so this just gives me an additional account that I need to keep track of. To calculate it, well, again, translational kinetic energy, that's just our 1/2 mv squared that we've been dealing with up until now. So up until now, we've been able to act like all of our objects are point particles, so we've only cared about how the center of mass has been moving. But with our rigid rotators, what we're saying is now I can also care about how the object rotates about the center of mass. And again, you notice that the form here is exactly the same, and I've swapped out mass has been replaced by moment of inertia, speed squared has been replaced by angular speed squared. We can also think about the work done by a constant force. We said that's going to be magnitude of the force times magnitude of the displacement times cosine of the angle between those two vectors. Well, I can also think about the work done due to a constant torque, because that's going to be the magnitude of the torque times the magnitude of the angular displacement times the cosine of those two vectors. And again, for us, with our angular problems really being one-dimensional problems, right, all of our directions are really along the axis of rotation. This is either a situation where the work is being done to speed an object up as it rotates, and so the torque and the angular displacement are in the same direction, or to slow down an object as it rotates, and the torque and the angular displacement would be in opposite directions. So we're either going to use 0 degrees or 180 degrees for our angle, which means that this cosine term is either going to be plus or minus 1. So the work done by a constant torque is going to be plus or minus magnitude of the torque times magnitude of the angular displacement. So we've up till now used gravitational potential energy. And again, since we've been able to act like the object was just a point particle, it hasn't really mattered where we've kept track of the gravitational potential energy from. But we'll notice that this does actually add a detail, because I can have both the center of mass and the other parts of my object move. And the thing to pay attention to is that the gravitational potential energy only cares about the change in height of the center of mass of the object. So here, right, if you can think of, say, maybe this piece of the ball that was at the top, well, as it rolled down and rolled down and rolled down, maybe when it gets to, maybe that same piece is at the bottom when it gets here. But gravity doesn't care about how the individual pieces are rotating about the center of mass. All that gravity cares about is just where did the center of mass start and where did the center of mass finish. So when we're working conservation of energy problems with rotational kinetic energy, we're going to do the same thing that we've been doing. We're going to pick a 0 point for the gravitational potential energy. It's going to be basically where the center of mass is at either the beginning or end. Here I've chosen it to be at the end, the lower point. And then the height that I care about is just the initial height of the center of mass before I let the ball go. So the only thing gravity cares about is just the center of mass when you're calculating your MGH. And so these are just, again, just the additional layers that we're going to add in to working conservation of energy problems now with rotational motion.